Hello there. Today we are going to continue with a discussion of polarity, and this time apply it to molecules. So in the last lesson, we talked about how to determine whether or not a bond is polar or nonpolar, and then we drew arrows or bond dipoles to represent polar bonds. That's something I want to specify because a lot of times we get caught up in the minutia of things, and I see from time to time that people still draw bond dipole arrows on nonpolar bonds. Now, I'll be honest, it's not a terrible thing because we know the only true nonpolar bond is something that's bonded to itself, but we don't really need to draw a bond dipole arrow in that scenario. The bond dipole arrow is there to represent a shift in the electrons towards one particular atom or one particular side of the molecule. So, that being said, when we're drawing arrows for our bond dipoles, we really only need to draw them for polar bonds. So, to determine if a molecule is nonpolar, we're first going to start out by drawing those bond dipoles, and then we're going to evaluate the direction that they are pointing. Now, when I say direction, the 3D shape is going to matter for figuring out where the bond dipoles are pointing. If they're pointing in the same general direction, we view those arrows as vectors. So when we add the vectors together, we end up with an overall net dipole for our molecule. So when we look at water, we see these two bond dipoles between H and O, and they're generally pointing towards the oxygen. If we were to combine those two arrows, we end up with a net dipole pointing towards the top of the molecule. When we look at the CH bonds, we know CH bonds are generally nonpolar, so we don't have any dipoles there, but we do have a dipole pointing from C to the F. There is nothing that is going to cancel out with that particular dipole, so that would also be considered polar. If there are no arrows, or if the arrows cancel out by pointing in equal and opposite directions, so the arrows would have to look something like this, then you could consider it a nonpolar molecule. Some hints, and it relates to the symmetry of the molecule. If you see a lone pair on your central atom, it will always be polar, even if the bonds appear to be nonpolar. There's another way we can do this by looking solely at symmetry of our molecule, but honestly, it is a lot more to remember. You do have to memorize which shapes are considered symmetrical and which are considered asymmetrical. But the issue with it is that it kind of takes away the understanding of what polarity is. When we're using bond dipoles, you're able to see clearly that there's a shift of the electrons towards one particular side of the molecule. So if you see a symmetry argument in other resources, that's certainly okay to do that, but that kind of puts it in a categorical box rather than actually thinking about what's happening with the electrons in my molecule. So using bond dipoles is a better way to do that. If we look at our first example, the CH bonds here are not polar, so I don't need a bond dipole there, but I do need one from my carbon to my chlorine. Chlorine, if I look back at an electronegativity table, chlorine is at a value of 3.0, whereas carbon's at a value of 2.5. The electronegativity difference there is 0.5, so I know that is a polar bond. If I look at the bond dipole that I have here, it does not have any other dipoles in the molecule, so the arrows are pointing in one direction in this case, and I can label it as a polar molecule. When we look at CF4, I see that F has a value of 4.0, C has a value of 2.5, so I get some really polar bonds here. 1.5 is my difference between my F and my C. So if I were to draw arrows here, I've got one pointing this way, one pointing this way, one pointing out towards me in the plane of the paper, and one pointing away from me out of the plane of the paper. So if I evaluate my second criteria here, do the arrows all point in the same direction? The answer is no. I've got one pointing up, one pointing to the side, one pointing away, and one pointing towards me. So in this particular scenario, it is said that they are all going to cancel out. Since they all cancel, this is going to be a non-polar molecule. Now, this is interesting. It's non-polar even though the bonds themselves are polar. So you can have polar bonds but still be non-polar as a molecule. So polar bonds is not always a sign that we are going to be polar. What is always a sign that we're going to be polar is if you've got that lone pair on the center of your atom. With water, if we redraw water here and actually put the lone pairs in, you'll see that you've got lone pairs up here. While it does look like I have a plane of symmetry down the middle of my molecule, I don't have a plane of symmetry going this way. So those dipoles don't have any way to cancel out. They have to combine and form a net dipole towards the oxygen molecule. So because of these lone pairs preventing us from being symmetrical, I do end up with a polar molecule. There are several other practice problems here that we can look at. So PCl3, if we actually drew the Lewis structure here with PCl3, I'm going to avoid putting electrons on all of my structures here. I'll do it for this first one, but I really want to focus on the central atom. I know I have a lone pair right here. This is a trigonal pyramidal shape. PCl3 is interesting because if you look at the bonds and the bond polarity here, Cl is 3.0 and phosphorus is 2.2. That is a difference of 0.8. So those are polar bonds, but there's no way for them to cancel out. All of these bonds and their dipoles are generally pointing the same direction. It looks like we have two pointing off to the side and one pointing toward us, but generally they are pointing down. So since they are pointing down and there's no way to cancel them out, this would also be a polar molecule. Water is one we just discussed. We know we've got two lone pairs here. Our dipoles are going to point towards oxygen because it's more electronegative. So this would also be a polar molecule. If we look at the CO bond, I've got a value of 3.5 for oxygen, 2.5 for carbon. Remember, I got to subtract the higher value from the smaller value. That bond is going to be polar, and they're both going to point towards oxygen with the higher value. But here, my arrows point in equal and opposite directions. They cancel, and I end up with a nonpolar molecule. On the next couple of practice problems you're pretty much doing the same thing. It does help to draw the 3D shape. So for 3D shape, a reminder, wedges versus dashes. If you are turning something from a 2D Lewis structure, say CH4, for instance, you got your 4 bonds. This is flat when we look at it on paper, but if we put it into 3D, we know we form a tetrahedral shape. We form that tetrahedral shape. 2 of those atoms are going to be in the plane of the paper, but the other 2 are going to have to be represented with a wedge and a dash. The dash goes backwards out of the plane of the paper. The wedge comes towards you in the plane of the paper. This matters most when looking at trigonal, pyramidal, and tetrahedral shapes. With linear shapes, we know they're all going to be in the same plane. When we're looking at trigonal planar, it's called planar because they all fit in the same plane. When we're looking at even the bent shapes, the bent shapes usually only have 2 atoms, but they've got those lone pairs. So these are even in the same plane. So really, we just care about using wedges and dashes with these particular shapes, and that will help you assess whether or not the dipoles cancel out. Okay. So on these next few, you see that some of them we've already adjusted for 3D shape. The CH bonds I know are not polar, so I don't have any bond dipoles, but I do know it is a tetrahedral shape. Since there are no bond dipoles, this is nonpolar. If I go on to the next one, I know CH again is not polar, but I've got this C double bonded to O, and that is a very polar bond. Those dipoles do not cancel, so with this trigonal planar shape, I get a polar bond. If I look at CS2, C and S bonds are actually fairly close to each other, I think, in electronegativity. If we go back to our electronegativity table, I see an S bond is 2.5 and actually carbon's 2.5. So this appears to have an electronegativity difference of 0, which is interesting because if we look at our electronegativity differences there, I don't have any dipoles here. Even if I did, they would point in equal and opposite directions. So either way you spin it, this one is a linear molecule with the same things attached on each side, and it has to be non-polar. Go on and try the rest for yourself, and we will check back in our next lesson. Have a great day.